Hello and welcome to G Fun Facts Online. Imagine a key that could unlock every digital door in the world. Every bank account, every government secret, every private message. This key isn't a fantasy. It's a theoretical possibility on the horizon, powered by a revolutionary technology called quantum computing. Today, we're going to explore this incredible new frontier, what it is, how it threatens to shatter the foundations of our digital world, and what we can do to prepare for the quantum age. So what exactly is this game-changing technology? At its heart, quantum computing is a fundamentally new way of processing information. Your phone, your laptop, every computer you've ever used works on the principles of classical computing. Information is stored in bits, which are like tiny light switches. A bit can be either a 1, representing on, or a 0, representing off. Simple, binary, and incredibly effective for decades. Quantum computers are different. They use something called a qubit. Instead of being just a 0 or a 1, a qubit can be a 0, a 1, or both at the same time. This mind-bending property is called superposition. Think of it like this. A classical bit is a coin lying flat on a table, either heads or tails. A qubit is like a coin that's still spinning in the air. It's a blend of heads and tails until you measure it, at which point it collapses into one state. This ability to exist in multiple states at once allows quantum computers to process a vast number of possibilities simultaneously. If you have two classical bits, you can have 4 possible combinations: 0, 0, 01, 10, or 11. But a classical computer can only work with one of these combinations at a time. 2 qubits, however, can represent all 4 of those combinations at the same time. As you add more qubits, the power grows exponentially. With just 300 qubits, a quantum computer could represent more states than there are atoms in the known universe. This is where their unbelievable computational power comes from. There is another strange quantum property called entanglement, which Einstein famously called spooky action at a distance. When 2 qubits are entangled, their fates are linked. No matter how far apart they are, if you measure one, you instantly know the state of the other. It's like having 2 of those spinning coins, and the moment one lands on heads, you know the other, even if it's on the other side of the galaxy, has just landed on tails. This interconnectedness allows for even more complex and powerful computations. Now, this power isn't for browsing the internet faster or playing video games with better graphics. Quantum computers are specialized machines designed to solve very specific, incredibly complex problems that are simply impossible for classical computers. We're talking about things like discovering new medicines and materials by simulating molecules with perfect accuracy, creating new financial models to manage risk in ways we can't imagine, or developing hyper-efficient logistics for global supply chains. They could help us design new catalysts to capture carbon from the atmosphere or create new types of batteries. The potential for good is immense. But with great power comes great risk. And that brings us to the dark side of quantum computing, its ability to break cryptography. Cryptography is the mathematical science of keeping information secret. It's the invisible armor that protects our digital lives. When you see a little padlock icon in your web browser, that's cryptography at work. It secures your online banking, your credit card payments, your private messages, and your emails. It also protects critical infrastructure, military communications, and sensitive government data. Most of the encryption we rely on today, systems like RSA and elliptic curve cryptography, are built on a simple premise. They use mathematical problems that are very easy to do in one direction, but incredibly difficult to reverse. For example, it's easy for a computer to take 2 very large prime numbers and multiply them together. But if you're only given the result of that multiplication, it is astronomically difficult for a classical computer to work backward and figure out the original 2 prime numbers. We're talking about a task that would take the world's most powerful supercomputer billions of years to complete. Our entire digital security framework is built on the confidence that this factoring problem is too hard to solve. But here's the terrifying part. In 1994, a mathematician named Peter Shor developed an algorithm, now called Shor's algorithm, specifically for a quantum computer. And this algorithm is designed to do one thing exceptionally well: find the prime factors of large numbers. A sufficiently powerful quantum computer running Shor's algorithm wouldn't take billions of years to break our encryption. It would take minutes, or perhaps even seconds. Every secure transaction, every encrypted file, every secret communication protected by this type of cryptography would become instantly vulnerable. The consequences are hard to overstate. It would be a digital apocalypse. Financial markets could be thrown into chaos as secure transactions become impossible. National security would be catastrophically compromised, as decades of classified intelligence could be unlocked. Critical infrastructure, like power grids and water supplies, which rely on secure communications, could be targeted. Your personal emails, health records, and private data could be exposed for all to see. The trust that underpins our entire digital society would evaporate. Now, you might be thinking, okay, but these powerful quantum computers don't exist yet, right? And you'd be correct. We're not there yet. Building a large-scale, fault-tolerant quantum computer is an immense scientific and engineering challenge. Qubits are incredibly fragile and sensitive to the slightest disturbance from their environment, like tiny vibrations or temperature changes. But major tech companies like Google, IBM, and Microsoft, as well as nations around the world, are pouring billions of dollars into this race. Progress is happening faster than many predicted. And this leads to an even more immediate danger, a strategy known as harvest now, decrypt later. Hostile governments or sophisticated criminal organizations are almost certainly already capturing and storing vast amounts of encrypted data today. They're siphoning off everything from corporate secrets to classified government cables. This data is useless to them now, but they are stockpiling it, waiting for the day they get their hands on a quantum computer powerful enough to decrypt it all. This means that data we think is secure right now is already at risk. The threat isn't a distant, future problem. The danger is already present in the data being harvested today. This brings us to the global race for what's called quantum supremacy. Not just building a quantum computer, but building one that can outperform any classical computer on a specific task. This is a geopolitical race we cannot afford to lose. The nation that first develops a large-scale, fault-tolerant quantum computer will have a tremendous strategic advantage, both economically and militarily. The security of our digital world, the stability of our economies, and the safety of our nations are all at stake. So what's the solution? Are we doomed to a future of digital chaos? Thankfully, no. The same community of brilliant mathematicians and cryptographers who saw this threat coming have been working on a defense for years. The solution is called post-quantum cryptography, or PQC. PQC is the development of a new generation of cryptographic algorithms that are designed to be secure against attacks from both classical and quantum computers. These new methods aren't based on the prime factorization problem that Shor's algorithm can solve. Instead, they're based on different, more complex mathematical problems that are believed to be hard even for a quantum computer. The U.S. National Institute of Standards and Technology, or NIST, has been running a global competition since 2016 to identify and standardize the best of these PQC algorithms. After years of intense scrutiny from experts worldwide, they have selected a suite of new cryptographic standards ready for deployment. The challenge now is the transition. We need to upgrade the entire global digital infrastructure. Every piece of software, every server, every router, every smartphone, every website, every single thing that uses encryption will need to be updated to use these new PQC standards. This is a monumental task, far larger than previous updates, like the Y2K problem. It will require a concerted effort from governments, industry, and academia. We must act now to prepare for this quantum future. This means investing heavily in research and development, not just in PQC, but in quantum technologies in general. It means fostering public-private partnerships to ensure a smooth and rapid transition. Companies and organizations need to start auditing their systems today to understand where their cryptographic vulnerabilities lie and begin planning their migration to PQC. The time to act is now. The quantum revolution is more than just a technological shift. It's a fundamental change in how we understand and manipulate the very fabric of reality. It offers us tools to solve some of humanity's greatest challenges, from disease to climate change. But it also presents a profound threat to the world we've built, a world that runs on data protected by codes that could soon be broken. We are standing at the threshold of a new age of information. The line between science fiction and reality is blurring before our very eyes. The work we do over the next decade, the research we fund, the standards we adopt, and the systems we upgrade will determine the character of this new era. It is a race we must win. By embracing both the challenges and the opportunities of the quantum revolution, we can work together to build a future that is not only technologically advanced, but also prosperous and secure for everyone. Thank you for tuning in to G Fun Facts Online. Join us next time as we explore another fascinating corner of our world.